We're going to talk about lesson 5-1. We're going to talk about trigonometric identities. Up until this point, we've talked about the 6 trig functions, and identities are a different type of mathematical idea. The idea of an identity is when the left side is equal to the right side of an equation for every single value of the variable when both sides of the equation are defined. So remember, we have some rules about some places where they're undefined, and we'll talk about those as we get to them. But first, let's look at trigonometric identities. We're going to start with reciprocal and quotient identities, and they're kind of the same idea, but not really, right? We're going to talk about reciprocal and quotient identities. They're exactly what they sound like, though. A reciprocal identity is an identity that takes its form from the reciprocal of the original function. So for example, we know already that cosecant of theta is equal 1 over sine theta. So the same reciprocal identity of that would be that sine of theta equals 1 over cosecant of theta, right? Because that's the reciprocal identity. Similarly, secant of theta is equal to 1 over cosine of theta, and cosine of theta, therefore, is equal to 1 over secant of theta. The same is true, of course, of cotangent. Cotangent of theta is equal to 1 over tangent of theta. Let me back that up really quick and undo since my pen got stuck. Tangent of theta. All right, let me get a new sheet here. We're going to do some quotient identities. Quotient identities are the ones that are written already as a quotient. So those, of course, are tangent theta and cotangent of theta. Tangent of theta is sine over cosine, right? And so therefore, its reciprocal, or its quotient identity, is 1 over cotangent of theta, which becomes then sine over cosine. Okay, ran out of space there on the end. And cotangent is similar. Cotangent is originally cosine over sine, and so its quotient is 1 over cotangent of theta, which is cosine over sine. I just noticed that I made a mistake up there. I need to go and correct. I think I said cotangent, or I think I said tangent, but I definitely did not write it. And so this, of course, should be tangent and not cotangent up here. All right. So these identities are pretty straightforward. Let's look at some Pythagorean identities. Of course, you know already that a right triangle with its legs and hypotenuse, are done by, if I have a right triangle, then what I'm looking at is that the legs and the square of one leg plus the square of the other leg is equal to the square of the third leg, right? The square of one leg plus the square of the other leg is equal to the square of the third leg. There's my shapes. Yes, right triangle. All right, so here's a right triangle. Well, let's suppose that on this right triangle that I have some lengths, and let's say that the length of my hypotenuse, let me use a different color here so you can see it, that the length of my hypotenuse is 1. Okay, if the length of my hypotenuse is 1, and let's say that somehow, magically, this ended up on the unit circle, where this leg is actually the 1 unit, right? So this is the radius equals 1 on your unit circle. So if you can imagine that, if I'm looking here, let me see if I can draw that for you. If I'm looking here at the unit circle, and I'm going to just draw a smaller version up here. If I'm looking here on the unit circle, I'm looking here at the radius being 1. Okay, so that's not perfect, but it's close. So I'm looking at my radius as 1, And so what I want to see then is, remember, the x value from side to side is sine. So this value down here at the bottom leg is going to be, I'm sorry, the x value is cosine. So the x value of this bottom leg is going to be cosine of theta. And this up and down value, this y value, is sine of theta. Okay? And so now I have this way of creating this Pythagorean identity. The Pythagorean identity is that if I square one leg and I square the other leg, then it equals 1, right? So it's going to look like this. It's going to say sine squared of theta plus cosine squared of theta equals the length of that hypotenuse, or 1 squared, right? So this is a Pythagorean identity. It's a Pythagorean identity because it comes from the Pythagorean theorem, okay? There are two other Pythagorean identities that I want you to know, okay? And you can derive them yourself. I'm not going to derive them for you. Or if you want me to derive them, you can come and ask me another time. But those other two identities are tangent squared theta plus 1. Tangent squared theta plus 1 is equal to secant squared theta. And cotangent squared theta plus 1 is equal to cosecant squared theta. Now these are none, and I'm going to go ahead and add that original one down here. The thing I like about these is that you can use them to solve different calculations when you're given certain parts and you don't know the entire triangle, which certainly you are going to need to be able to do. So let's do one just for fun, or just because we have to. All right, so let's do one. So let's suppose that you're given this information. The tangent of theta is -8. Okay, and you have some information here. The tangent of theta is -8, and you're given this, that sine of theta has to be greater than 0, and that they want you to find, so they're going to ask you to find, we want to find sine of theta and cosine of theta, right? So let's go back to that last page and look at those identities for a second. Which one do you want to use? Well, I have a tangent, and I need to find sine and cosine. Well, we know from our original set of identities that these are all related, and so when we get down here and we want to try and solve, what we want to do is pick the one that gives us tangent so that we can find maybe another one using one of those identities, right? So we know that tangent is sine over cosine, right? We know that already. We also know from this last slide that tangent theta plus 1 is secant squared theta, and we know that secant is equal to 1 over cosine, so that's going to come in handy. So let's use that identity. We're going to say that tangent squared theta plus 1 is equal to secant squared theta. Okay? Tangent squared theta is equal to secant squared theta. So let's plug in the numbers that we know. We know that tangent here, we know that it equals -8, so we're going to use that. Let me switch my colors back here. So it's going to equal -8 squared, okay, plus 1 gives me secant squared theta. Gives me secant squared theta, right? And so we know that -8 squared is 64. 64 plus 1 is equal to secant squared theta, which is 65. So we know because of this then that secant theta must equal positive or negative. I'm going to run out of space there. Let me put that somewhere else so that you can actually see it. Secant theta then equals the positive and negative values of the square root of 65. Okay, keep that in mind. I hope you're taking good notes here so that you can keep that in mind so that we can move on to the next part of the problem. So I know now that secant theta is equal to plus or minus the square root of 65. Now, we were told on the previous slide that we want sine of theta to be greater than 0, right? Sine of theta needs to be greater than 0. So because sine of theta needs to be greater than 0, then we know that cosine theta must be less than 0. And how do we know that? We know that cosine theta has to be less than 0 because if sine of theta is greater than 0 and tangent is negative, then cosine must be negative if the sine is positive. So now we know this. Because secant theta is 1 over cosine of theta, then we know that it has to be the negative version of it, right? So we know then that secant must be negative the square root of 65, since we know that cosine must be less than 0. Okay, if secant theta then is negative the square root of 65, okay, and tangent theta is equal to sine over cosine, right? Tangent theta is sine over cosine. Remember, the original problem asked us to find both sine and cosine, okay? If we know that tangent is sine over cosine, and we know that secant is negative the square root of 65, then we know that cosine, because of our reciprocal identity, right? Cosine, because of our reciprocal identity, must be 1 over negative the square root of 65. And we know that because earlier, right, we remember that it is the reciprocal of secant, right? So if the secant is negative the square root of 65, then the cosine must be the 1 over negative square root of 65. I know that tangent is negative 8. So let's fill in what we know so we solve what we don't. I'm going to put in negative 8 for tangent here, and it's going to be sine theta over 1 over negative the square root of 65. Okay? So obviously, since you're dividing, what I see here actually is that I can multiply both sides by 1 over negative the square root of 65, which is exactly what I'm going to do here, right? So sine of theta then, which is what we're looking for, becomes, sine of theta becomes sine of theta becomes actually the two values multiplied by each other. But I want you to look up here because I made a mistake. I made a mistake as I was sitting there and my voice disappeared. I realized that I made the mistake because I wrote that cosine is 1 over negative the square root of 65, and that is actually not correct, right? Cosine is actually, no, that's right. I'm sorry, that is right. That is 1 over negative square root of 65. So sine of theta is actually 8 over the square root of 65. Now, in your book, you might see that that was actually rationalized, and so it actually ends up being this value, right, because they rationalized the denominator, right? So this is the value for sine theta. We're going to stop there for now, and we'll cover some of the rest of the identities when we come back to class another day.